So is the microphone working? Testing, testing, okay. So I think it's time to begin. Our speaker is Xuwen Zhu from Northeastern University in Boston, and she will be talking about analysis of gravitational instantons.
All right, well, thank you very much. I would like to thank the organizers for giving me the opportunity to speak here, and thank everybody who is still here for the talk. And so today I'm going to talk about some recent progress in the analysis of a few types of gravitational instantons, which is a very popular field currently and has seen a lot of exciting development. And my talk will mostly be about what we brought to the fields using geometric Mark-Local analysis as an analysis tool, which gives us more geometric ingredients for this subject. Okay, so here's my the talk outline. Well, first of all, I'm going to talk about what is gravitational instantons and to talk about some basic properties of this object. And then one of the main analysis ingredient in this talk will be we'll develop the Fredholm theory of the Laplace operator. And in particular, I'll talk about what the Laplace operator look like and what kind of tools we're going to be using for analyzing this. And then, as an application of the Fredholm theory, we can obtain some geometric information of the gravitational instantons, which include L2 cohomology, asymptotic expansion, and moduli space of gravitational instantons. And the last part of the talk will be, so it's related to, you can say, the third part of the application, the moduli space. So once you have a moduli space, you start thinking about the degeneration of moduli spaces. What are the boundaries? And so the last part will be a new construction of a degeneration sequence of ALH star gravitational instantons. Okay, well, let me start by talking about the basic. So we start with a classical theory. So a Calabi-Yau manifold has the following properties. It's scalar, it has a Ricci flat metric, and in particular, it has a special holonomy in SUN. Okay? And so that's an n-dimensional Calabi-Yau. And so for us, one of the things that's interesting for Calabi-Yau is that in real dimension 4, a Calabi-Yau manifold has not only a Taylor structure. Doesn't work. Okay. All right. Okay. Where did I lose you? Right, they're trying to track me, I guess. Okay. Right. So besides one Kähler structure for a dimension 4 Calabi-Yau manifold, it actually has a hyper-Kähler structure. So it's a quaternion structure of Kähler structures. So in particular, what this means is that there are 3 complex structures, I, J, and K. They satisfy Ij equal to K, Jk equal to I, Kj equal to okay, well, you know what's the next one. And in particular, with the spanning of the 3 complex structures will actually get you an S2 of complex structures because you can do a linear span of the 3. So this is something called hyperkähler rotation, and it's a special structure in dimension 4. And in particular, dimension 4m, but for us, we're going to be interested in dimension 4. And in this dimension 4 case, the reason why this Calabi-Yau manifold will have this special structures there because there is an accidental equivalence between this SU2 and SP1. Those two are the same. And having a special holonomy in SP1 will give you the hyperkähler structure. Okay, so while Calabi-Yau manifolds has seen, well, it's a rich subject and still a lot of things are going on. And for the compact Calabi-Yau case in 4 dimension, a real 4 dimension, we know that there are 2 types. One is the 4 torus, and the other one is the case-free surface. And okay, are the case-free surfaces. On the other hand, that we're also interested in the non-compact ones. So I'll talk a little bit later why we care about the non-compact ones. So the non-compact analog of the Calabi-Yau manifolds are called gravitational instantons. So, well, what are those? Well, the gravitational instantons, they are given by non-compact and complete hyperkähler 4 manifolds. And so this is, you can say, we need some non-compact end, but this end should be complete. And moreover, at the end, you need to have some structure, which is we need to control the curvature. And the curvature, usually when we say curvature decaying fast enough, and usually we say L2 curvature. Depends on different people. Some people will have more general definitions. But usually when we say gravitational instantons, these are L2 curvature decay at the end. Okay, well, why do we care about those things? So one of the reasons for the appearance of gravitational instantons is that they themselves appear as moduli space of solutions to gauge equations. So in particular, monopole equations and other gauge equations. And the non-compact end appears when the gauge equations have some particular boundary conditions or some kind of degeneration, and then you have the limit going to the infinity, and that's where we see it. And another major reason for the appearance of the gravitational instantons is that one can use this as bubbles or building blocks for gluing constructions of case-free surfaces. So it's you can say similar to in the real two-dimensional case, in the Riemann surface case, when you have the moduli space, and then you think about what happens when the Riemann surface, when a family of Riemann surfaces degenerates, well, you get nodal surfaces. And here, what we're thinking about is what happens if you take a family of case-free surfaces, and when it degenerates, what happens? And it turns out that a lot of such degenerations can be characterized as some points of the case-free surfaces will have the curvature blow up. And if you zoom into the blow up points, you'll see those bubbles, which are exactly those gravitational instantons. Yeah. Yeah. Mm-hmm. I would say cusp metrics. So hyperbolic metrics with cusp singularities. So that's I mean it's not quite an analogy, especially if you think about the gluing construction, because there's gravitational instantons. You can say that. I guess a good analog would be cusps. So they're like the bubbles when you
under the hyperbolic.
That's right, under the hyperbolic metric. Yeah. So it's those points when your curvature or some kind of singularity will appear in the limit of the degenerating sequence. And in the four-dimensional case, of course, there are a lot more different kinds of singularities will appear, and those are the gravitational instantons. And in two-dimensional case, if you keep the hyperbolic structure, then the only thing happens is cusp. Yeah. Okay. So that gives a bit of motivation of why we study the gravitational instantons, and this will come back later. And now let me talk about what are the gravitational instantons. So the infinity structure really tells us a lot about gravitational instantons. And in particular, there are four well-known types of infinity structure. So the first one is called ALE, which stands for asymptotically locally Euclidean. So this is really saying that the end is modeled by R4 or a quotient of R4. And in particular, the order of gross infinity is like R to the fourth. And then the second type is called ALF, which stands for asymptotically locally flat. And the local model is given by R3 cross a circle bounded over R3 or a quotient of that. And in particular, that the volume growth at infinity is like R to the 3. And then, well, there are two more types that's with volume growing even slower. So that's volume growth R squared and volume growth R. And locally, it's modeled by S2 cross R2 or S1 cross S3 cross R. Those two stands for ALG and ALH, and the G and H doesn't mean anything. They just follow the name E and F. So those are the four well-known types of infinity structures of gravitational instantons, and it's known by the work of Minervi and Chen that if you assume your curvature decay is slightly better than L2, meaning there's extra epsilon there, then they show that all the non-flat gravitational instantons is one of the above. And that's it. Yeah. Mm-hmm. Yeah.
if I think of cusps under the hyperbolic metric on the Riemann surface. So in that case, if I want to think of this volume growth, that would be just measure the length of the Hurry cycle near a cusp.
Interesting question. I mean, the problem here is that the gravitational instantons they are rigid metrics, and the hyperbolic ones just the curvature is different.
Yeah,
right? So when you think about the growth,
analog of
right? The volume growth just doesn't make sense.
Sure.
Right.
The volume should be considered within the area of the hyperbolic surface, or just the length of the Hurry cycle. I mean, I'm just trying to get a comparison. Does not have to.
I mean, my guess is that if you really want to think about comparison, then we probably should think about some flat structures on the Riemann surface, which of course
still
you
the
have.
volume is the area, or the volume is the.
Well, then you'll have, say, a cylindrical end or some other end, which is more of a like flat structure on Riemann surface.
You want to measure the growth of the area of this kind of cylindrical ends.
Right. Well, I mean, there is really in the Riemann surface case, there are only, you can say, two possibilities in some sense. There's R squared and there's R, right? It's either you're just going to have an R2 end opening up to infinity like a cone, or you have a cylinder going to infinity. So I think that's but of course the problem is that your original surface, it's going to be a Riemann surface with flat metric. It will be a flat surface.
Yeah.
Right. So you need to have something in here. But I think in terms of volume growth at infinity, it's going to be. So it's actually similar to this one. So this ALE is kind of like you have a cone structure at infinity. And this LF is circle over cone. And then so it's you have a more higher and higher dimension of circles and the torus over cones. Okay. Now, what's surprising is that it turns out that there are two more types. And if you just weaken the curvature condition to remove the epsilon, so it's like exactly L2 condition, then there are two more types. And the recent work on Xuwen and Zhang, they actually show that that's it, that everything is contained in the 6 types. And I won't say too much about ALG star, and we'll talk more about in detail in ALH star. But those names comes from that they are, in terms of volume growth, they are ALH star is going to be between G and H, and ALG star will have exactly the same volume growth as ALG, but different curvature conditions. Okay. Yeah.
Examples of these in the physics.
Yes. So currently, I think the progress is that all 6 types of gravitational instantons have been realized as moduli space of some kind of monopole equations. But these monopoles might be like SU2 monopoles or U1 monopoles or the doubly periodic monopoles. So depending on different boundary conditions, then you'll realize them as different types. I mean, I don't think at all every gravitational instantons have been realized, but I think the conjecture is that they can be done, and it's being done currently. Right. So, So in this talk, what in this talk, we're going to focus on one particular type called ALH star. So it's a relatively newer type. And so one particular example of this ALH star gravitational instant is called Tianyao matrix. I'll say a bit later. And so it satisfies the condition that the curvature decay is exactly at R to the minus 2, and the volume growth is this funky number 4/3, which is between 1 and 2. And so there's just like we want to understand what are those things as moduli spaces of gauge equations. And those gauge equations, they can kind of merge into each other. So the conjecture is that all those gravitational instantons, their moduli space should be pieced together in a huge moduli space, where some types are the boundary of some other moduli spaces. And so there are works going on about the degeneration. And so one of the earlier works is by Ray, who showed that ALE and ALF can be related. So more or less the intuition is that if you start with an S1 cross an R3 cone, then you can open up your S1 to enlarge it, and bigger and bigger, and eventually you're going to get R4. So that's a degeneration. And there's a joint work with Yu-Shen Lin and Sidharth Soundararajan that we're working on the degeneration between ALH and ALH star and ALG and ALG star. And again, the conjecture is that all the 6 levels of gravitational instantons, they are related in each level, and they're also related across levels. Yeah. That's right. Yeah. Yeah, there's a, yeah, I'll say that in a moment. So Sergei Cherkis has a, and I want to say Kapustin, and Cherkis and Kapustin and their collaborators, they have constructed a few types, in particular those well-known ones, those ALE and ALF ones. They realize those, there's some kind of, you can relate those gravitational, each of gravitational instantons as moduli space of some kind of algebraic structures. And then the degeneration of the algebraic structures is related to what happens when this monopole has some kind of boundary degeneration. And then this will merge between different types of gravitational instantons. So I will say that a little bit later. And in particular, in the ALH star case, it's related to this Del Pezzo surface. Okay. Now, well, let me say a little bit of what exactly structure is for the ALH star, because it's kind of a funky structure. That so in general, that for a gravitational instanton, there's a well-known ansatz called Gibbons-Hawking ansatz. That if you have a hyperkähler structure, which is at infinity, and if you have an S1 symmetry there, then you can realize this as a circle bundle over a flat manifold. Now, when I say the circle bundle is really it's not exactly a circle bundle in the sense that it can degenerate. There are singular points, but in most of the places it's just really circles. And the way to do it is that you use the circle bundle and then take the harmonic function on this flat 3 manifold. And this harmonic function should satisfy condition here, this quantization condition. And then one can generate a metric using this form here, which that if effectively it's a word product, that you have the flat metric, and then it's weighted using this V, and then you have the circle direction. The theta is a connection on the circle, and then the weight is V to the inverse. And now, of course, you can imagine that if V has some kind of singularities, then this metric could have potential singularities, and usually cut it off. Okay, so I'll talk about a few known examples. The first example is R4. So R4 is a standard ALE space, asymptotic locally Euclidean. And the way to think about it, in this, if you want to write it in the Gibbons-Hawking ansatz, we can write it in the polar coordinates. And the way to do it is you start with an R3, and then take a circle bundle over R3, and then take the harmonic function as 1 over 2R. And then, well, you'll have 1 over 2R on R3, and then times R times d theta squared. Yeah. This G is metric. That's right, yeah. So this is like d theta squared, and this is like dx1 squared plus d2 dx2 squared. That's right, yeah. So this is it's a metric form. And you can use this Gibbons-Hawking ansatz to write out the Kähler form. And to write out, there's something called hyperkähler triples. And the information are all here in containing this V and this theta here. So here, if we are in this case, then this is really just R4. And the only thing is that this vibration is a Hopf vibration. At infinity, you have an S3 vibrating over S2, and that's a Hopf vibration. Now, yeah. Aha. Right. Yes, there are multi-centered ALE spaces. That's right. Yeah. That's right. Yeah. So in particular, there's a famous space called multi-Taubnat space, which is you can take a harmonic function with multiple singularities, and then you can piece them together. You also get an ALF. That's right. In fact, a huge class of ALF comes from this kind of connecting different, just put in a different harmonic function. Yeah. That's right. You can have multiple singularities. Right, so as I said, that if you just adjust the harmonic function by adding a constant here, as long as the sigma is non-zero, then it becomes ALF. that at infinity you'll get an R3 across an S1 structure. And then there's the trivial situation when you have a T2 cross R and then take the trivial harmonic function 1. And in this case, well, it's really just the base is T2 cross R, and then you have another S1 direction, which has a d theta squared. So this is going to get you T3 cross R, which is a standard ALH space. Okay. Now, let's talk about a little bit about the structure I want to talk about. It was ALH star. So here is the base is the same, the vibration is the same. That you have U is this T2 cross R, but instead of V choosing the constant, we choose a different V. We choose the harmonic function here, where this Z variable is a variable R. And once you do that, then you'll see that one can write out explicitly the metric, which I'll write out on the next page, and then you can compute the volume growth and the curvature decay. And you'll see that it falls into this ALH star. Okay, so now the reason, as I said before, that one of the reasons we want to study gravitational instantons is that they arise as bubbles for degeneration of case-free surfaces. And one of the things for algebraic geometers, in some sense, case-free surfaces are more known because you can write out your algebraic equation and then you know that those are the case-free surfaces. Now, on the other hand, from a differential geometric perspective, that we know that there is a Ricci flat metric there. And by Yau's theorem, that you can solve the Monge-Ampere equation to get the Ricci flat metric, but it's not explicit at all. That it's actually quite hard to write. I don't think there's any explicit expression of what this case-free metric looks like. So one of the motivations for this is that we want to try to understand what the metric is by looking at what happens when it's near degeneration. Because when it's near degeneration, these gravitational instantons are pretty explicit. So via gluing constructions, you can see that when the case-free surfaces are almost collapsing into some lower dimensional objects, near those degenerating limits, the case-free surface, the Ricci flat metrics can actually be written out explicitly. And yeah.
The bubble, they're always CP1.
Oh no. When I say bubbles, it's just bubbles. It's they don't have to be CP1. They can have topologies there. Yeah. So this gravitation, right? I should say that the interior, or the compact part of the gravitational instanton can have different topologies. And they're actually characterized by that. So
they have some.
They can have
structure.
Right. I mean, at infinity, they don't always have bound. That at near infinity, it's always asymptotic to this kind of circle bundle over some. And you can have topologies there because you can have a group action. But on the other hand, you also have interior cycles. So those bubbles doesn't have to be CP1, and they are. Well, I mean, they're not CP1 because of dimension. They're actually real four dimension. So they are.
Oh, yeah.
Right, they are degeneration. That's right. They're degeneration for real four-dimensional manifolds. That's right, singular four-dimensional manifolds. That's right. Yeah. Yeah. So, yeah. That depends on the Euler characteristic. I think it depends on the topology. So I think at least for all the works that's listed here, there are some number that you count how do you get to the Euler characteristic. And for example, so for the work of say Fons Kahlo's work is gluing ALF spaces into so that the family of case-free surfaces would degenerate into a two torus. Well, not quite a two torus, but it's a two-dimensional circle over a line. And then in this process, of course, while your original case-free surfaces has non-trivial Euler characteristics, it has to go somewhere. And that's where those bubbles will eat up those Euler characteristics. And the number of bubbles will need to satisfy this condition, the topological condition there.
Yeah.
Just one chance. Okay, let me see. So this Chen and Chen is I believe it's Gao Chen and Xiuzhong Chen, and I think this Chen is also Gao Chen, and Zhang is Ruobing Zhang, and well that's right. I believe those are the two Chens that's in this business.
Right, the Chens,
Right. Wow. That's right. Yeah. Okay, so those are some of the works that's using gravitational instantons as bubbles, and there are also more recent works that's appearing, and I think the basic idea is that all gravitational instantons can be realized as some bubbles of degenerations. And depending on the degeneration limits, whether it's codimension 3, codimension 2, codimension 1, then you will use different bubbles. And another thing I want to mention is the recent work of Tristan Zuk and also the work of Isfahani and Li. So those are not really using, they're also kind of degeneration, but it's a degeneration of different types. So the Tristan Zuk's work is degeneration of Kähler-Einstein metrics, and not necessarily keeping the K3 structure. And there also he used the gravitational instantons. And the work of Isfahani and Yang Li is, again, degenerating of K3 cross some higher dimensional objects, and where the gravitational instantons is again bubbling the bubbles. So as I said, that K3 surfaces, at least from the differential geometric perspective, is quite mysterious. That's just not explicit. So we want to use what happens near the boundary of the moduli space to see like the interior points. So one of the things that we can do is to show that that using bubbles, we can show that there is a neighborhood near the boundary of K3 surfaces, such that each of the K3 surfaces there contains a non-holomorphic minimal sphere, meaning that it's an area, it's a two-sphere, so it's a submanifold. It's area minimizing and stable, and it's not holomorphic with respect to any of the hyperkähler structures. So this is something related to this so-called weak gravity conjecture by Vafa, that this is one of the interpretations that in Calabi-Yau manifolds there should have some kind of non-BPS particles in some kind of large complex limits, and so this is one of the situations that one can prove that. And so I should say that this work is so some cases of the K3 surface are already known by the results of Foscolo, and the work hopefully will be posted in the next 2 days, is that we can generalize it to a bigger neighborhood of the moduli space, because it turns out that there are more gravitational instantons having this property, so we can use those bubbles to glue in and get this.
But in Arabic geometry, there are different ways to compactify the moduli space of K3 surfaces.
Right.
Which moduli space we refer to?
Right. So here, when I say this moduli space, we are thinking about this 58 dimension of the Ricci flat matrix there. That's the differential geometric perspective. Yeah, that's right. Yeah. Okay. Now let me go to the main object, which is this ALH star. So as I said before, this is it's yeah.
That's this minimum space of
is it a Lagrangian? No, I believe it's actually exactly the non-Lagrangian. There is a particular gravitational instantons called Atiyah-Hitchin space, which is an ALF space. So this is modeling some monopoles. And then for this Atiyah-Hitchin metric, it turns out it's explicit, and you can write out explicitly, and you can compute that there is this one sphere, which is just the orbit of this SU2 action there, and this one is just non-homomorphic. So I don't think that one is Lagrangian. Yeah. And then everything else follows from that. You can glue this Atiyah-Hitchin metric to produce more gravitational instantons as bubbles, and then you put more of those bubbles into K3. So you have a lot of those. Right. So that was one of the motivations for doing this. Now let's talk about ALH star. Okay, so I want to say a little bit about the analysis of this metric. So for this one, it's at infinity, the structure is fairly straightforward, that you can write out everything explicitly. That in particular, well, what I'm going to do is so we have this we have 4 variables in some sense, that we have the y1, y2, which is on T2, and we have z, which is on R, and then we have another variable here. The theta is a circle variable, and then so that's the metric, and the weight here is just the z. Now, what I'm going to do is I'm going to change variable to change out z, because in the original in the original limit, we're letting z go to infinity. That's the end. I'm going to change it to 1 over x, so that x is going to 0. That's just easier to see what the metric looks like. So in particular, we can write it out in this way, and then you'll see that there are three parts of the metric, 3 levels of metric, and each of them is shrinking or expanding in different ways. And this is what it makes difficult to analyze because of those weird weights. So the picture is here that, that I'm already using this x picture, so x is going to 0, and that's the end. That's the end, the infinity. And in this process, for each fixed x, there is a T2 vibration, S1 vibration over T2, which is actually a neo Heisenberg neo manifold. But let's just say that's look like that. And then on the T2 direction, this is here, which has a 1 over x factor, which is going to infinity. So the T2 is expanding. On the other hand, the red one is the circle direction. The circle direction has an x factor, which is going to 0. So the circle direction is shrinking. So in the end, you can say if you compactify it, you can add in a T2 there to add infinity, because that in the end you have this one dimension is collapsing, and then the other dimension is going to infinity. So that's a picture, and this metric is explicit, but it turns out that the analysis takes some time. So before I go on, I should say that one of the first examples of analyzing realizing an ALH star is called Tian-Yau metric. So this is by the work of Tian-Yau. They showed that you can construct a Ricci-Flat Kähler metric by solving a complex Monge-Ampere equation. And the way to do it is you take a smooth Fano manifold, take out a smooth anti-canonical divisor, and then put an n structure near the divisor, which is called Calabi-Yau ansatz, which in dimension 2 case, in complex dimension 2 case, is exactly this Gibbons-Hawking ansatz. And then you solve the complex Monge-Ampere equation to get the exact Ricci-Flat Kähler metric. So that's we're not going to use this too much. We're just using this as a black box in the sense that we know there are such metrics. And for this particular ALH star, there are, let's say, a few types of appearance. So one of the first appearances of this is they appear as a building block in the codimension 3 collapsing of K3 surfaces. So this is, if you start with a family of K3 surfaces and squash them to a line, it's just a segment 0, 1. And then this is the work of Han Sun via Kosaki Zhang. They showed that if you rescale the bubble, if you rescale it back, you'll see that there are a few places where the curvature blows up. And those are 3 different types of things, well, 2 different types of things. The 2 ends are given by exactly this gravitational ALH star. And then in the middle, there's something called a multi-top nut metric. So that's one gluing. That's where this ALH star happens. And okay, thank you. So there are more appearances of the gravitational instantons. So this is a work of recent work of Collins, Jacob, Lin. In a series of work, they show that you can use this as one example of SYV symmetry. That they show that there is a mirror symmetry pair between 2 types of metrics. One side is this Tian-Yau metric, and the other side is called, under hyperkähler rotation, you have something called the generalized semi-flight metrics, which is another way to write out the gravitational instantons. And during this hyperkähler rotation, your Lagrangian manifold is rotated too. So this is one of the explicit examples of SYV symmetry. And that's also one of the reasons we were also interested to understand everything about this ALH star. And yeah, I think so. There's some. I mean, I think SYV symmetry in general is related to the T duality. So there's a. I'm not sure here in the physics picture there are exact definite description of the 2 sides yet, for in terms of T duality, but at least the theoretical nature. Another thing I want to mention here is that there are Torelli type theorems for this ALH star, which is you can compactify them to get weak del Pezzo surfaces. So that's the work of two teams, Collins, Jacob Ling, and also Heinz Via John. And so that's we're not going to use it too much, but eventually when we're talking about the degeneration of ALH star, this kind of weak del Pezzo surface will make an appearance back. And another thing I want to mention is that, as I mentioned before, that most of the gravitational instantons can be interpreted as some kind of moduli space. So here, Cherkis had worked to interpret ALH star as some kind of monopole equations with complicated boundary conditions. And he can show exactly that when this condition degenerates, or in some way going to infinity, that this is where the ALH star will come out. Okay. All right. Now let me talk about where we got the problem. So it turns out that, well, in the gluing construction of this 4-person paper, one of the keys is to study the Laplace operator. And they did a lot of work there to show the mapping properties. And also there's also a later work by Xuwen Zhu to the general higher dimensional Calabi model of the Lugos theorem. But one thing they couldn't do was to develop the Fredholm theory. And that was where we got the problem from them. They asked if we can have some tools to study this. And of course, in a lot of if you want to study more in detail of this metric, Fredholm theory of the Laplace operator is useful to get the deformation and Hodge theory. So that's why we are interested to get the Fredholm theory. And now it turns out that in this type of singularities is one of the singularity structures that can be studied systematically using geometric microlocal analysis. That we can deal with this kind of inhomogeneous collapsing. And so this is one of the things that we'll do. And but before that, let me just give a list of results. That's hopefully this one also will be appearing in the next few months. That for an ALH star metric, this is a joint work with Rafe Mazzeo. We can show that you can have Fredholm property. You can actually get Fredholm, but the price to pay is that you can't use regular Sobolev spaces. That you need to have weighted Sobolev spaces, and also the Sobolev spaces should have some kind of special boundary regularities when you're going to infinity. This is and it is cooked up to observe the structure of the ALH star. And then the next three are, you can say, corollary of the first one. Is that you can compute the L2 harmonic forms, and this can be identified with some kind of topological forms, which is called intersection cohomology. And then one can show that all ALH star metrics has a very nice asymptotic expansion at infinity. And then the last thing is that we can show the local perturbation of metric in terms of hyperkähler structure. They can be identified with boundary data and interior data in some way that you can explicitly write out. Okay. So let me go back to the Laplace operator. I want to at least show a little bit that where the difficulties are and how do we deal with that. Okay, so so this Laplace operator is just with respect to this local coordinates, and everything is explicit, at least locally. And what I would do is we would multiply an x in front so that we don't have an x inverse factor here. Okay. And so this Laplace operator has a main part and has a lower order part. And the main part will have three things. So that's where I'm going to go to the next page. Okay. So we'll focus on the first bracket here. So there's an x6 to partial x square, which is, you can say, spanned by the vector field of x cubed dx. And then there's this x squared partial y, which is on the t2 direction, and it's spanned by vectors x partial y1, x partial y2. And then there's this partial theta direction. Okay. So there are three directions: the s1 direction, t2 direction, and r direction. And the vector fields they have different rate of decay at infinity. So this is a structure that very similar to some other structures called fiber boundary or fiber cusp structures, and that appears in other types of gravitational instantons. And that was studied by Matteo Melrose, Vaillant, and also Hunziker-Matteo in this ALE and ALF case. And but this one is not quite a fiber boundary or fiber cusp structure. It's something more complicated called an A structure, where A is, it's developed by Grieser and Hunsaker, and A stands for a vector, which is telling you that you can have several vibrations, several levels of vibrations. And on each level, your metric can have a different weight in front. Okay. So you might want to say that it looks fairly explicit, that why can't we just do it explicitly? You can. In this particular case, indeed, that if we just want to study this particular one and forget about the lower order terms, that for this one itself, you can do it explicitly by separation of variables. If it's a product structure. So, I mean, one of the problems for us here is that you do have the lower order terms, and this is not a product structure. But if we just focusing on the three things here, that you can do it, and what you'll see is that, well, when you're doing the separation of variables on the S1 direction, on the T2 directions, then you will see different things coming out. So this is, on the other hand, if we want to study more systematically, then what we can do is to see that, well, there are three parts. So I'm going to use the projection of the d theta part and projection of the dt part. So the first thing we can see is that if you just project off if you assume this function is on the zero mode of T2 and zero mode of theta, then you just don't have those two terms. And then this Laplacian is just given by x6 partial x squared, which is a one-dimensional boundary operator, one-dimensional singular ODE operator. And that one can study it. And a fancy way to say this is that it's x to the 4 times a B operator, which is given by x dx square. But you can study it. Now, a second part is that if we're assuming that we're going to project off to the non-zero modes of T2, but still projecting off the d theta, then you have this x6 and x squared term, and then this is something called a cusp operator. And then if you have all the terms here, we'll have a fully elliptic operator. Okay, so, well, let me say a little bit of how do we develop the Fredholm theory part. So I won't be able to do this for the ALH star, but I want to show at least the basic idea of this geometric microlocal analysis. How do you get the generalized inverse? So the basic idea is that, well, if you want to show some operator is Fredholm, there's only one thing we know, which is identity plus a compact operator is Fredholm. That's it. So, and now if you can find a generalized inverse which satisfies that G composed with this and Laplacian composed with G, they are both equal to identity plus some kind of compact operators. Then this side is Fredholm, and then you'll be able to show that both the Laplacian will have both finite dimensional kernel and cokernel just by composition. Okay, so that's where this construction of the G will come in. So this is we want to compute the inverse of a differential operator. Now, one way to do this is to study the Schwartz kernel of the differential operator. So and instead of writing it for this more complicated space, I'm going to start with a one-dimensional simple case. So we're going to do a simple model case, a toy case, where we are on just zero infinity. And this operator P is a B operator. It's given by x d by dx plus c, where c is can be a complex number. But for now, I'm going to assume that c is less easier. Okay, so this is this is a trivial problem that you're just solving an ODE with the right-hand side. And to solve the ODE, you can actually write out explicitly. And for this one, you just integrate it. And then we'll see that, well, this ux can be written in terms of f. So you just integrate this x dx plus cf, u equal to f. And then this can be written as the following: 0 to x of x to the minus c, x prime, c minus 1, f x prime, dx prime. So here, this is really just explicitly write out, and this x prime is the variable that's going to be integrated out. And I should say that here I cheated a little bit. I chose the Dirichlet boundary condition so you don't have another term. So that we have, if you don't choose a boundary condition, then there's no way you can find an inverse. You just have a family of inverse. Okay, but for now, let's say it's Dirichlet boundary condition, then it's written like that. And now I'm going to write it as from 0 to infinity of chi x prime less than or equal to x prime over x to the c, and f x prime dx prime over x prime. Okay. So again, this is nothing. I'm just rewriting everything into a more uniform format, and then writing the integration over the whole matter. And in general, that this is going to be a pseudo-differential operator as an inverse of a differential operator. And the way to think about it is that, well, U is going to be equal to QF, where Q is this operator that maps F back to U. And this QF is explicitly written here that you feed in F here, you integrate it against the kernel, which is called Schwartz kernel, integrate it out to the X prime variable, then you'll get the X variable, which is a function. So this is a Schwartz function and a Schwartz kernel of a differential or pseudo-differential operator. And there's general theory to tell us that this function on this double space, which is meaning that it's a function of both x and x prime. It contains all the information you need for the mapping properties of the differential operator. Okay, so well, now let's look at the function more carefully for this particular one. And so for this one, the space is going to be x and x prime here. And now, well, there are two types of singularities here. The first type of singularity is this cutoff function. This cutoff function has a jump singularity along the diagonal, because this is just chi x prime and less than or equal to x. And now, if we're assuming c less than 0, then the cutoff function also has a singularity at x prime equal to 0, which is here. Okay. So there are two singular lines coming in, and the space, so meaning that this function is singular on the two sides, and in particular at this point, there are two types of singularities coming in, and they merge at the same place, which is annoying because there are two types of one is a polynomial singularity, and the other one is a delta type singularity. So one solution to that, in order to see what it really looks like, is that we're going to introduce polar coordinates at this point. And effectively, geometrically, what we're going to do is we do blow up. And so if we introduce polar coordinates at the point 0 here, then it replaces a point by a quarter circle. And the diagonals and this axis here is going to lift up to this here and this here. And in particular, they're going to be separated. And in terms of local coordinates for this one, it's actually quite easy to see that. So this kappa x prime, the local coordinates here can be chosen as t equal to x prime of x and x. And then this is a kappa is going to be chi of t less than or equal to 1 and t to the c, which is two types of singularities, but they are completely separated. Okay, so this is an example as like a philosophical demonstration of what's going on for finding the inverse. So if we're just solving a problem like that, you might as well just integrate like that. The problem is that in general that you can't, once you get into PDE, there's no way to integrate like that. So, but the general phenomenon, it turns out to be the same. That usually the Schwartz kernel in the original double space will have certain singularities. And in particular, usually there are two types of singularities. One is the diagonal, which stands for the differential singularity. And then you have the boundary irregularities here, which is on the boundary. So, and usually they meet somewhere. And and in order to really understand what's the mapping property, it's better to introduce a blow-up, meaning introducing polar coordinates, to a new space where the different types of singularities are separated. And the benefit for doing this is that under the new coordinates, you can construct this inverse here and here separately. And then you can patch them together. Unlike in this case, well, you have a corner here. We don't know whether we should come down here or we should come down here. So that's a geometric point of view of what we're doing. And I should say that, so this type of blow-up depends a lot on the geometry, or you can say the infinity structure of this Laplace operator. And for example, that A operator will have 3 levels of different singularities, so you need to do a few levels of log. But all in all, what we're doing is to introduce new coordinates so that you can separate the different parts of construction and patch them together later. Okay. And I should also say that if you're more familiar with, say, usual elliptic estimates, there's actually an interpretation of what we're doing here, is to say that for general elliptic estimates, so the general elliptic estimates is that, well, you have a u, let's make the two pu plus another u, I mean, there's a c here. That if p is an elliptic operator of some order, it's hk here, and then it's hk minus s here, minus n here, for example, and then this h minus n. I'm just using some numbers. Okay, so the point is that you want to know that the right-hand side should boost up the solution's regularity. And if it's compact case, then we already have a good Fredholm property, because there is this h minus n on the compact manifold actually sits compactly inside hk. And that's a problem the problem with non-compact manifolds is that it's no longer compact embedding. And that's why you need to put in weights and put in stuff. And now this type of blow-up, in some sense, is saying that, well, we can construct better and better inverse so that every time we can introduce a better and better space here until the space sits compactly here. And in general, it involves 2 parts, that you need to first deal with the differential order, which is a diagonal, and then you'll need to deal with some kind of weights here, which will deal with the boundaries. Okay, so that's more or less the idea of the geometric microlocal analysis, at least in the elliptic part, is that we do blow up, and which corresponds to finding better elliptic estimates. Okay, so to do this, well, the theorem is that one can do this for this complicated A structure. I'm not going to write out the blob for there because it's just there's no point to do that. But you just have to trust me that introduce some kind of polar coordinates, you can do that. And then one can show that you can construct parametrics so that things are Fredholm. Okay, let me see. 8 minutes. Okay, great. So once we have the Fredholm theory, well, we have the L2 cohomology. I think I'll skip most part of that. I just want to say that the general motivation for this kind of L2 cohomology of non-compact space is that you want to use L2 cohomology to detect the behavior at infinity. So one of the those are 2 examples of if we use the same space, which is simple space at 1, 0, 1, but use different metrics. One is the usual Euclidean metric, and the other one it has a degeneration, which effectively is saying that if you use an exponential map, you can pull back this 0 to infinity to 0, 1 using this metric. And then under those 2 different metrics, the L2 cohomology, which is using the L2 cochains, then you'll get different dimensions. And the ones on the right is the usual one, that for a 0, 1 space, H0 is R and H1 is 0. On the other hand, if on the left, the problem is that a lot of functions are no longer L2. For example, the constant is no longer an L2 function with respect to the metric. And basically because of this reason, you'll see that those 2 are like that. So that's one of the reasons that you can get something slightly different, and which contains information about the metric. Okay. So so one can use the I think I'll just say that the idea is that once we have the Fredholm theory of the Laplacian, which can also apply to Fredholm theory of the Dirac operator, one can compute the harmonic forms, and there is this interpretation here that the L2 harmonic forms can be identified with those spaces. Some of them are intersectional cohomology. Some of them are just the regular relative cohomology. So it looks a bit ugly, and unfortunately, currently we do not have a good interpretation of what they are. So unlike in the ALE and ALF case, it turns out that one can compute the L2 cohomology, and you can actually identify it nicely there, and you can compute the dimension. And you can show that it corresponds to the moduli space of ALE and ALF. For the L2, for the ALH case, currently we still don't have a very good interpretation of what they are, but at least we can compute it. Okay. And Okay, I think I'll skip that. So that's with Fredholm theory, we can compute the asymptotic expansion. And then the next thing I want to say is, so one can do the perturbation of this hyperkähler matrix on the ALH star, because it turns out that there is a way to set up this equation so that it's a nonlinear equation, but the leading order terms are just the scalar Laplacians. So once you have a good mapping property of the linearized operator, then the perturbation comes in. And now I want to use the last 5 minutes to say a bit about the moduli space of what happens when it degenerates. So first of all, we know that the moduli space of ALH star, well, I should say that there is this number B that I didn't quite mention before, but it corresponds to the number of, you can say, monopoles or cycles, how many cycles you can have in the interior. And so each of the ALHB star will have a moduli space. And but the space is non-compact. And just like in the case 3 case, that depending on how you parameterize it, there are different ways to degenerate. And so the one work is this collapsing limit, which is done by Lin and Takahashi. And now the ones that we are interested in is to keep the dimension, but you want to degenerate in other types. So as I mentioned before, that a similar case is that you can degenerate ALF to ALE. And in our case, we construct the following sequence of degenerations, which is starting from ALH, which can be viewed as ALH star 0 in some way, because that's in the limit. And then you can have a sequence of degenerations like that. And what it means is that you can take a family of ALH, and then in the Gromov-Horsdorff limit, it can go into ALH star 1. And then you can take a whole family of ALH 1 star, and then it can degenerate to an ALH 2 star. And there are 9 types of ALH star, and they're all in. And in some sense, you can view this as a bubble tree structure. That just more and more things pop up. And I should say that the intuition here is that there are a number of monopole singularities in the ALH star, and this number 9 minus b is the number of monopoles. So in the degeneration, what happens is that when one monopole travels to infinity, then you jump to the next level. So that's more or less the intuition. And now, if all the monopoles disappear into infinity, then your topology gets very simple, and we get an ALH 9 minus 1. So I should say that this kind of degeneration is related to this del Pezzo surface degeneration tree. So I think that's more in algebraic geometry that there are 10 types of del Pezzo surfaces. I want to say there's right, because when b equal to a, there are 2 types. One can because of the Torellis theorem of AH star, that you can view each of them can be compactified into a del Pezzo surface, and you have this tree structure of one degenerates into another and one degenerates into another. And correspondingly, this is a related picture. And it's already realized in some kind of algebraic way by Cherkis. So that's one of the things we could do. And now let me just say a little bit about the intuition. So the intuition is that if you start with an ALHB minus 1, then you can view this as a gluing construction of two things. One end is this ALHB, which has an end like that, because this is the S1 cross T2 thing. And then there is a neck, which has the Taubner singularities. And what happens is that we can construct a family of such ALHB B minus 1, such that this neck is getting longer and longer and thinner, and this point is getting farther and farther away from this ALHB cap. And of course, what this means is that in the end, you are going to get the degeneration, which is going from a family of ALHB minus 1 into only the cap, because this neck will disappear into infinity. So that's more or less the intuition. And so for the actual proof, what we did is to do in the case-free version, just because compact manifolds are easier to deal with. So what we constructed is a family of case-free surfaces where you have 2 levels of degeneration, where one of them is coming from this original bubble, and this bubble is getting another bubble. So there's this double bubbling structure. And this is the ongoing work with Yu-Shen Lin and Soundararajan. We can show that there is this Gromov-Force-Bidorf limit, and this gives us a partial compactification of the ALH and ALH star moduli spaces. And in particular, the higher number serves as a boundary of the lower number of moduli spaces. And there's also a similar construction of ALG and ALG star case. And I should say that in terms of analysis, what happens is that we're still going to do a gluing construction. And that's where the Fredholm theory comes in again, that because in the gluing construction, eventually we're going to do a perturbative argument to find the actual solution where the linearized operator is exactly the Laplacian. So in the singular space, mapping properties can be useful. All right, so that's everything I want to talk about today, and thanks very much.
Questions?
So when you say there exists a sequence converging to the limit,
Yeah.
I mean, how much does the limit depend on the sequence? And for example, usually when we talk about moduli space, we want it to be proper, like separated, and
So very good question. So here, the sequence we constructed, they are, you can say it's like they're perpendicular to the boundary of the moduli space. You're just shooting in towards the moduli space, and so that's they are how do I say? In terms of okay, let's just say that in terms of period domain, that what happens is that one of the periods will go to infinite, and in the process, and that's just like this is this codimensional 1 degeneration.
Any other questions? So if there are questions online, you have to unmute yourself because we cannot see the chat. Well, so if there are no questions, then let's thank the speaker again.
Thanks very much.